Hi all, welcome to part 2 of the audio mixing and mastering workshop. This part is going to cover analog versus digital. So we'll start off with analog. An analog signal is a signal that's analogous to some real-world quantity. So in the context of sound, usually that's going to be an electrical signal, a voltage, and it's going to be analogous to the sound pressure, which is the real quantity we're trying to measure. So for example, a microphone might convert sound pressure into voltages, electrical signals, that can be measured or amplified. And a guitar pickup might convert the displacement of metal strings into voltages that can be measured or amplified. And analog signals are continuous in all domains. That's what differentiates them from digital signals. For example, a microphone's voltage is continuous in the voltage and time domain. So that might be more clear on a graph here. This red line represents the analog signal that we're trying to measure. And when I say it's continuous in all domains, I mean that if you pick 2 points on this red line, you can always zoom in and find a point in between them. It's smooth, it's connected, and there's no kind of discrete point where it jumps. Now, digital signals are discrete in all domains. So there's a discrete number of samples per unit time. So in between these 2 blue points here, I don't have any data. All I have is these discrete samples because we're sampling every set amount of time. And it's also discrete in the domain of the value that we're trying to measure. So not just in the time domain, but in between 8 and 9 here, there's no possible value. And we can kind of see that at the top here. Where we got to the top, these 3 points were all labeled 15 because 14 would be too low, but there's no option in between. And that's an inherent characteristic of digital signals. There's a discrete number of choices to record to. Our mixer uses analog to digital converters, ADCs, to convert this analog signal, in this case an analog voltage, so what's represented by this red line, from audio sources into digital samples, these blue points, using PCM. And I've kind of written it out in a technical way here, but if you look at the graphic, hopefully it's understandable. All it does is it takes a sample of this red line, so in this case it recorded 8. It quantized it to a discrete value. For the purposes of this presentation, you can think of that as rounding. So it took a point on the red line, rounded it to 8, recorded it, and then it waited some amount of time, and then it did it again. So then it sampled 9, then it waited some amount of time, and then it recorded 11, and then it waited some amount of time, recorded 13, and it just does that. And it does it every 1 over fs seconds, where fs is that sampling frequency. So for example, we could sample at 48,000 times per second, in which case between each of these samples we're going to have 1/48,000th of a second where we're waiting before we take a new sample. So it's a thing in the analog domain as well, but because there's some maximum possible value and minimum possible value, because there's only a finite number of values in a digital signal, what happens if the analog real-world signal goes above that maximum or below that minimum? Well, what will happen is the waveform will become just chopped off. And so instead of having a smooth curve at the top here, the top will get flattened. And this is called clipping. And you can kind of imagine the root of that word. It kind of clips the top of the wave off. And this sounds bad. So we want to avoid this when we're working with digital audio and analog audio for that matter. But in this context, it's more important to focus on digital clipping because that's what we'll be dealing with. So when it comes to PCM data, PCM is again that algorithm where we take a sample every fixed amount of time. there are two, what I would say, relevant variables. There's other variables, but these are the two most relevant. The first one is the sampling rate or the sampling frequency. So how often do we take a sample? We could take one once every 44,100 or 44,100 times a second. We could take a sample. Or we could take a sample 48,000 times a second. So how often should we take that? I'll discuss that in a bit. The bit depth determines how many possible values there are for each sample. So in this case, we had 16 possible values. And that means we had a bit depth of 4. The relationship between the bit depth and how many possible values you have isn't super relevant. It's 2 to the b. If you have a background in computer science, the bit depth just tells you how many bits of data each sample contains. And so if you have integer encoded PCM, the number of possible values is 2 to the b. And if you don't understand that, it's totally fine. But just know that more bits means more resolution on this axis. So instead of having 16 possible values, if we had a bit depth of 5, for example, we would have 32 possible values. And then these points at the top here, we had to round them to 15. Maybe we could get a more accurate representation of each point if we have a higher bit depth. The two most common bit depths are 16-bit and 24-bit. They offer dynamic ranges of 98 and 146 decibels respectively. And for people who are familiar with the decibel scale, you'll realize these would be quite loud. And because this is the ratio between the loudest sound a digital audio track can produce and the quietest sound a digital audio track can produce, unless you're listening at unsafe volumes, 16-bit is more than enough for listening. But because we might need to do amplification in post, and we just want to retain as much quality as possible, all raw recordings and masters should be exported to 24-bit. But if the underlying recording was 16-bit, 16-bit is fine, because you're not going to lose any data in that case. But 24-bit doesn't take up that much more space than 16-bit, so we're going to want to use that for recordings. Now, in terms of the sample rate, I posed that question of, how high of a frequency should we use for sampling? And there's a theorem that says if you have a given sample rate, the highest reproducible frequency is half of that sample rate. The theorem is a little more complicated than this. There's some requirements, but for the most part, it's true. And given that the human range of hearing ends around 20 kilohertz, sample rates far above 40 kilohertz are generally excessive because all you get from that is the ability to reproduce frequencies that we can't hear. The two most common sample rates are 44.1 kilohertz and 48 kilohertz. 44.1 kilohertz is the standard for CDs, but because 48 kilohertz divides nicely into video frame rates and because YouTube recommends it, make all recordings at 48 kilohertz. That's our kind of standard sample rate. Now, this is not entirely true, but because resampling changes the underlying data, old 44.1 kilohertz recordings, I would master them at 44.1 kilohertz. But if you upsample them to 48 kilohertz, it's actually not really that big of a deal. But 48 is going to be our default. So that's it for this part of the series, and I'll see you in the next one.